Thank you. Science of Santa, a relatively short talk, and I've given it a few times, but I don't think I've ever had Santa in the audience before whenever I've given it. So this is a new one for me. So, I'm asking the question, is Santa compatible with the laws of physics? I'm a scientist, I'm a physicist, so I wonder, is Santa real? Or does he break enough laws of physics that we can declare Santa cannot be real? So how many laws of physics does Santa actually break? That's what we're asking. So we know that Santa is, well, at least allegedly, a portly, jolly fellow with a white beard and a penchant for wearing red suits. Yeah. But even though that is rather questionable fashion sense, that doesn't mean he cannot exist. So what about the claims made about what Santa is supposedly doing each Christmas? Can we actually use our knowledge of science to say that's possible or impossible? So we know, I guess, the story. He visits all households on Christmas Eve to deliver presents to all qualifying children. And how does a child qualify? Well, it depends on the naughty nice list, of course. So can we reconcile that statement that he visits all children on Christmas Eve? Can we reconcile that with our understanding of science? And in particular, I thought, of all of the science talks I've given over the years, of which there have been many dozen, can I use any of the information in any of the science I've given? Perhaps you recognize Apollo 13 from earlier in the year. Does any of that science help us understand this business about Santa? So let's examine what it is that he's supposed to be able to do. That is the sentence we're going to pick apart. Santa visits households on Christmas Eve to deliver presents to children. So first, let's start at the end. Children. How many presents does he deliver to how many children? So let's assume that the Earth's population is 8 billion. 25% of the Earth's population are children. And let's assume that, let's say, half of them are eligible to get Christmas presents. That doesn't necessarily mean they come from Christian households, but Santa is a quite kind old man, so he will deliver presents to other people as well. So about 1 billion children get Christmas presents. That's assuming that the naughty nice list is naughty equals 0 and nice equals 100%. Now, I'm sure there's some parents in the audience who might question that particular ratio. Let's just keep it simple. 1 billion children is what we're talking about. So, next part, Santa visits. So how does he get around? What's his mode of transport? Well, Santa, of course, is in a sleigh, as you well know, and the sleigh is pulled by flying reindeer. So, first question, can reindeer fly? Scientifically, can we answer that question yes or no? Well, we know that insects fly, and we know that birds fly and pterosaurs fly, though you don't see that many of them these days. And we know that mammals fly. So the question is, do reindeer fly? Well, if they can fly, they choose not to do so for a lot of the time, because nobody has actually seen them, and I don't believe anybody's actually photographed them flying. So there's very little evidence for reindeer being able to fly. But remember, scientists always come back to the mantra, absence of evidence is not evidence of absence. Just because we haven't got any photos of them flying doesn't mean they can't. So the jury is still out on that one. Okay, how fast would Santa have to go when he's doing these visits to all these places? Well, we can do a very simple calculation and assume that the various households are spread around the world. Of course, we know they're probably more likely to be concentrated in cities, but let's just assume they're spread over the world. We can calculate how fast Santa would have to travel in order to visit them all in 36 hours. 36 hours because Christmas Eve, remember, it's about 12 hours of night, depending on whether you're North or South Hemisphere. And let's assume he uses the time zone sensibly to go around the world. So that way he's got 36 hours to deliver the presents. But he would only have to travel at 2,000 kilometers per second. Now, that might sound very fast for those of you driving up the motorway, but actually 2,000 kilometers a second is quite slow. It's only a tiny fraction of the speed of light. And the speed of light is the only physical limit for any object moving through space. In a completely different talk, called Fiat Lux, let there be light. I talk about the nature of light and the fact that nothing can travel faster than light in a vacuum. The universe is expanding, and the universe is actually expanding faster than that. But in terms of traveling through space, nothing can go faster than light. But Santa isn't even close to breaking that speed limit. He's less than 1% of the speed of light. No problem whatsoever. But if he is traveling really fast, doesn't everything get really hot and you'll end up with roast reindeer? Well, why do things get hot when you move fast? A meteor coming into the Earth's atmosphere, or an asteroid, or a spacecraft coming into the Earth's atmosphere, some people think they get hot by friction. Strictly, no. Anything coming into the Earth's atmosphere moving really fast compresses the air in front of the object and the air gets hot. So surely, if the sleigh is moving at great speed through the Earth's atmosphere, it's going to compress the air in front of the object. Again, a different talk talks about the so-called ABC of how stars work. Stars get hot because gravity condenses a cloud, and the compression of that cloud heats up the star, and the star ultimately produces nuclear fusion to keep the star going. So stars are hot because of compression. So if you fly quickly through the atmosphere and compress the air, won't the sleigh get hot? And won't the reindeer burn up? Even if the sleigh is aerodynamic, even if it's really good, surely at 2,000 kilometers per second, it's still going to be very, very hot. Won't it glow like a supernova? Won't it be a really bright object? Because it's going to be so hot, surely it must be glowing white hot. Well, we know that in principle, compression produces heat. Hot things glow. Basically, if they're warm, they'll emit infrared light. If they're really hot, they'll emit a lot of white light. If they get really hot, they'll start to emit ultraviolet light. But basically, anything that gets hot emits light. So maybe that was what the Star of Bethlehem was. 2,000 years ago, a bright light was seen in the sky. Was that Santa's sleigh? Well, it's pushing it a little bit to say that Santa was actually responsible for the Star of Bethlehem, which presumably appeared before Christ was born. So the timeline is getting a bit mixed up there. But maybe a bright light in the sky, well, forget 2,000 years ago, a bright light in the sky, people are always seeing those. What do you think UFOs are? They're bright lights in the sky. Okay, they tend to get seen not just on Christmas Eve, but at other times of the year as well. So maybe that doesn't fit. But we do know about certain stuff, certain matter, which, when you heat it up, it does not glow. We have found out in the last few decades, when we look out into the universe, that there is stuff called dark matter. And dark matter is stuff that, unlike the stuff that we are all made of, when it gets hot, when you give it more energy, it doesn't glow. It doesn't emit any light. It doesn't absorb any light. It doesn't reflect any light. And here I'm using light in the general sense, infrared, visible light, ultraviolet, radio waves. None of that gets emitted or absorbed. So maybe Santa's sleigh is made of dark matter. That would explain why it doesn't glow even when it gets really hot. And as a sort of an aside, that also explains why it doesn't show up on radar, because it won't reflect any radar that's sent its way. It'll just go straight through. So that's different. That is glowing as if it glows. Yeah, as if it glows. So it's not actually glowing. Yeah, if you remember the lyrics of the song, you would even think it glows. Yeah, so it doesn't actually glow. Right. So, yes, I've given this talk before. So coming back to the statement, we've said that 1 billion children are visited. The visiting is done with a sleigh that goes really fast through the atmosphere, and it doesn't glow because maybe it's made of dark matter, or maybe there's some other reason. Let's think about the households that Santa visits. So how on earth does a portly, jolly fellow get down so many chimneys? He would have to go down something like 3,000 chimneys a second, which is tough for any of us, no matter how much weight we put on. So how can somebody who doesn't even fit in a chimney go down a chimney really fast? Well, here, quantum mechanics comes to our rescue. Quantum mechanics is the quantum theory of really small things, atoms, molecules, etc. And we know from what we understand of quantum theory that atoms are made of a nucleus and surrounding electrons. If you decide to replace all of the electrons with a different subatomic particle called a muon, then the atom will be a lot smaller because muons are much heavier than electrons. They're a sort of heavy cousin of electrons. So if you replaced all the electrons with muons, the atoms would be 200 times smaller, which means anything made of those atoms would be 200 times smaller. So instead of Santa being a little less than 2 meters tall, he would only be about 1 centimeter high. So he would drop down a chimney, no problem whatsoever. Dead easy. How you go about replacing electrons with muons, I don't know, but it's perfectly acceptable that that can happen. How he does it, well, that's still a little bit of a mystery, but that doesn't break any laws of physics.
If he's an inch high, how big are his presents?
We're getting to the presents. You're jumping the gun. But what if there are no chimneys? It's all very well saying he's small enough to go down the chimneys, but what if there aren't any chimneys? What if you're in a sealed house with closed doors and closed windows? Well, it is still possible for an object to go from outdoors to indoors without going through an open door or an open window. It's a phenomenon called tunneling. It basically means one solid object can pass through another solid object, and it doesn't normally happen. We don't see it generally in day-to-day situations, but it is not forbidden by the laws of physics. It's just relatively unlikely. But we're not talking about whether Santa is possible or impossible. The fact that it might be likely or unlikely is irrelevant. Somehow he's managed to find a way to do that. So this is allowable according to quantum theory, according to the fundamental laws of physics, that one solid object can pass through another. So he doesn't need an open window, he doesn't need an open door. The phenomena is called quantum tunneling, if you're interested in Googling it sometime. Okay, right, so Santa is visiting all of these households and getting inside quite easily, either down the chimney or tunneling through a solid wall. He does this on Christmas Eve, the 36 hours that we say that he's got to do this, all in one night. How does he do all of this visitation all in one night? Even at traveling at relativistic speeds, going at a fair old fraction of the speed of light, how can he possibly do it in 36 hours? Well, there's nothing to say he can't be in two places at once. I know normally that doesn't happen. One person is either over there or over there. But again, quantum theory tells us that actually an atom can be here and there at the same time. So if it's possible for an atom to be in two places at once, maybe Santa has figured out how to do it as well. And if you can be in two places at once, well, why can't you be in 1,000 places at once? Or 10,000? Or 1,000,000? There is nothing in the laws of physics that say you can't do that. It is very unlikely, but we're not talking about whether it is very probable or improbable. We're trying to work out whether it's possible or impossible. So being in more places at once than just the one is possible according to the laws of physics. And if you really don't like that, if for some reason Santa can only be in one place at a time, well, there are other possibilities as to how he manages to get round all of these households in the 36 hours that he is allotted. And that is, you bring the houses to you rather than travel to the houses. You want to get to 1 billion different places, but space can be warped. For instance, the Earth warps the space around it. The sun warps the space around it. Black holes warp the space around it. It is possible, but very difficult, to warp space so that you bring one house to you, deliver the presents, and then you bring another house to you, deliver the presents, etc. You don't have to go traveling to all these places. You can warp space and distort space to bring those various destinations to you. It is very difficult to do that. Just because I don't know how to do it doesn't mean he doesn't. So it is again not breaking any laws of physics. So we've had visitation to households, 1 billion children on Christmas Eve, and we come back to the gentleman's point. What about delivering all these presents? So how can he carry all of these presents? How big must Santa's sack be, if you'll excuse the expression? One present each. Let's assume that we don't have lots of presents per person. One each for each of 1 billion children. How can the sleigh hold 1 billion presents? Well, The sleigh is presumably a few meters or so long, a bit like your own sleigh. But objects can be bigger on the inside than they are on the outside. Now, I know you think that's science fiction because you all know about Doctor Who's TARDIS, but no, physics tells us that it is possible for an object to be larger on the inside than the outside. And when we think about the way black holes behave, we are fairly damn sure, though we haven't actually been there with a ruler yet, but we are fairly damn sure that black holes are bigger on the inside than on the outside. And therefore, well, okay, maybe Santa has got a little black hole on the back seat and he's using that to store all the presents. Alternatively, if you don't like the idea of storing all the presents in a black hole, I mean, how do you get them out again afterwards? That's part of the problem. Maybe there's other ways of distorting space so that you can find a volume that's bigger on the inside than the outside so that the sleigh is a lot bigger than it looks. But there's another possibility, and that is that so far as we know, space has got 3 dimensions: forward, backward, left, right, up and down. But there are many physicists who believe that there are actually more than 3 dimensions. It's just that we find it difficult to figure out what they are. It's difficult to actually come to terms with the fact that there might be more than 3. Where on earth are the other ones? We can't perceive them, but maybe they are there. Some physicists believe there aren't just 3 dimensions, there are actually 11. And maybe Santa has figured out how to use those extra dimensions. Maybe he takes all of these presents and simply moves them from the 3-dimensional space that we're used to, and he shoves them in one of the other dimensions. And then he goes visiting, and then he pulls them out of that dimension and delivers them to the various households. A little bit of a hypothesis there, but we cannot be sure. So we don't know that he breaks any rules by carrying 1 billion presents around with him. You might say, well, okay, you say this is not actually forbidden by the rules of physics, the laws of physics, but surely if he did any of these things, wouldn't it need an absolutely huge amount of energy to actually achieve this? If you wanted to distort space to bring the destinations closer to you, if you wanted to move at relativistic speeds through the atmosphere, surely moving Santa and a sleigh and 1 billion presents at high speed is going to take an enormous amount of energy. So how on earth can you claim that Santa can do this? Black holes again. If you had a black hole, the black hole would be smaller than a grain of sand. A black hole would provide enough power to travel to the stars, let alone push a sleigh around the Earth in 36 hours. So again, quite the technical challenge of harnessing a black hole is quite an achievement, but there's nothing to say it cannot be done. A small black hole, a tiny black hole, would actually provide a huge amount of power. But actually there's an alternative source. We don't have to resort to black holes in this context. There is a source of energy available to Santa during the 36 hours of him delivering presents. And it's the thing that we're ignoring. It's the elephant in the room. What have we not mentioned so far?
Solar powers.
What happens?
Solar panels in the roof, you know.
Time.
What happens to all the mince pies?
Oh.
Lots of people leave mince pies out for Santa. What happens to them all? Well, mince pies have mass. And we know from good old Einstein that mass and energy are interchangeable. You can take matter and convert it into energy. You can take energy and convert it into matter. The exchange rate, if you want to think of it that way, is the speed of light squared. E equals mc squared. So how much energy could you get out of a mince pie? We can do the calculation. If you don't like maths, look away now. Because we can say, right, if you take a 50-gram mince pie, which I think is about standard, a 50-gram mince pie multiplied by the speed of light squared gives you the energy content of a mince pie. And it is 5 times 10 to the power 15 joules. I'll come back to that unit in a moment because not everybody is familiar with that particular energy unit. Let's assume a few percent of people leave a mince pie for Santa. Just a few percent. Not everybody, just a few percent. Let's say 20 million households leave mince pies for Santa. That's 20 million mince pies multiplied by the number I've just calculated, 5 times 10 to the 15. That means the total energy available to Santa, if he can get the energy out of the mince pies, is a whopping 10 to the power 23 joules. One with 23 zeros after it. How much energy is that? Well, you can judge how much energy that is by thinking about, for instance, a nuclear power station. Sizewell B, something like that, generates gigawatts of power. Imagine all the energy it produces second after second after second after second, 24/7, all year, for 1,000,000 years. That is 10 to the 23 joules. So all of that energy, a nuclear power station running for 1,000,000 years, all of that energy is available to Santa in one night. Therefore, that's easily enough to send a sleigh at high speed or to warp space and time as he needs. How do you get the energy out? Saying that that energy is there is one thing. How does Santa get the energy out of the mince pies? So we know that equation is valid. That's one of the fundamental laws of physics that we've known about for 100 years. There are ways of getting energy out of matter. You can take a mince pie, and all you have to do is collide it with an antimatter mince pie. And you can do that, of course, in the Large Mince Pie Collider at CERN, which is built for that task. And that will give you all of the energy we're talking about. But of course, the problem is, where do you get the anti-mince pies from in the first place? So people don't leave anti-mince pies out for Santa, only the mince pies. So there's an imbalance there. So maybe this idea of a mince pie collider doesn't really work. There has to be another way of getting energy out of mince pies. And luckily there is. It's not quite as efficient. We can't get necessarily 100% of the energy out, but we can get a fairly good fraction of that energy out of a mince pie. By a fairly good fraction, I mean 10%, 20%, maybe even as much as 30% of the energy can be extracted by taking the mince pies and dropping them into a black hole. Black holes are the answer to everything, aren't they? We know, for instance, from looking out into the universe, that there are some black holes out there, and matter is falling into those black holes. Probably not mince pies. It's probably more likely stars are falling into those black holes and generating enormous amounts of energy. I imaged back in 2020 during a lockdown, I imaged a quasar, which is a galaxy in which matter is falling into a really big black hole. And I imaged that quasar, even though the quasar is billions of light years away, simply because so much energy was released when that happens, it was still possible to image that with a camera here on Earth, billions of light years away. So we know dropping matter into a black hole is an extremely efficient way of converting matter into energy. How well does it work with stars? We know it works very well. How well does it work with mince pies? I found it very difficult to find out. I searched and searched and searched for all of the research I could on the effect of dropping mince pies into black holes. Very few people seem to be working on that, but surely it must be quite an efficient way of doing it. Okay, it's possible, and there's all this energy available to make it possible for Santa to do this. But how has he got the skill set to actually do this? How is it that he could possibly, for instance, manipulate space and time? Even if we know it's possible to do that, even if you had all the energy at your disposal, how come Santa is the person that seems to be able to do this? Well, one thing to bear in mind is, who says Santa has to be human? Possibly. Is he a different creature with a Santa suit? I mean, no one's seen him. Kids are always asleep when he arrives, by definition, so we don't actually know. So maybe Santa has a skill set and has some abilities, much like Yoda, that we don't fully comprehend. So to come back to the original question.
Proof he exists.
You just
So-
read down those
He
chimneys like
looks
that.
like Yoda. Sorry, go on, carry on.
So to come back to the original question, is Santa compatible with the laws of physics? Or to turn it around slightly, just how many laws of physics does Santa actually break? I think the answer is none. So feel free to draw your own conclusions about the existence or otherwise of the portly, jolly fellow with the white beard. with a penchant for wearing red suits. And regardless of what conclusion you come to, may I wish you all a very Merry Christmas.
Are you open to questions?
Yep.